Superconductors can be classified into two: type 1 superconductors and type 2 superconductors. Type 1 and type 2 superconductors. Type 1 superconductors have a sharp critical point, or the response to the magnetic field is very sharp in the case of type 1 superconductors. Type 1 superconductors are also called soft superconductors. In type 1 superconductors, the magnetic field will be, the superconductivity will be destroyed completely at the critical magnetic field. Example, mercury, tin, etc. But in the case of type 2 superconductors, the magnetic field starts to penetrate inside the material at a temperature, at a magnetic field Hc1, which is normally less than the critical field Hc, and at another critical field called Hc2, which is normally higher than the critical field Hc, the flux penetrates the material completely. This Hc1 is called lower critical field and Hc2 is called upper critical field. So, between these two critical fields, Hc1 and Hc2, the material is in a mixed state. This Hc2 is normally very much higher than the critical temperature Hc, as approximately 100 times or about 400 times higher than the critical field Hc. And this property or this phenomenon, that the upper critical field is much higher than the critical field Hc, makes such materials favorable for technological applications, like in the case of NMR spectroscopy or in the case of MRI scan, etc. Between Hc1 and Hc2, the material forms small superconducting regions surrounded by normal regions. Such regions are called vortices or fluxoids. Vortices or fluxoids. And due to the formation of vortices or fluxoids, the surface energy of the material becomes negative and the material can withstand more critical field. And the reason for that is the material has too short coherence length. I will discuss about coherence length later. Now, we know from uncertainty principle, delta x, delta p is of the order of h cross. We know this uncertainty relation is true not only for this x and p, but for all canonically conjugate variables like energy and time, like angle and angular momentum, etc. See, instead of x, I write coherence length lambda, then lambda into delta p is of the order of h cross, or lambda of the order of h cross by delta p. Let that be relation number 1. We know the kinetic energy E is equal to p square by 2m. If I differentiate it, delta E is equal to 2p into delta P by 2m, or delta E is equal to P delta P by 2m. Or delta P is equal to 2m delta E divided by P, and we know delta E is equal to kT from thermodynamics, where T is absolute temperature, and in this case we can write Tc, which is superconducting transition temperature or critical temperature, and if I substitute for delta E here, we get delta P is equal to 2m kTc. Let that be relation number 2. If I substitute this expression in 1, we get lambda is equal to h cross divided by 2m kTc. Here h cross is constant, 2 is constant, m is constant, k is constant, Boltzmann's constant, and lambda inversely proportional to critical temperature. That is, as coherence length decreases, the critical temperature or superconducting transition temperature increases. That's what I told earlier. In the case of type 2 superconductors, the coherence length is too short. Since the coherence length is too short, the critical temperature is much higher, and much higher critical temperature makes possible for the use of such materials in technological applications. London equations. On the basis of Maxwell's theory or Maxwell's equations alone, it is not possible to describe the properties of superconductivity completely. Therefore, Kastler and Gotte proposed a two-fluid model in which two types of electrons exist inside a superconductor. The one is called normal electrons and the second one is called superelectrons. The normal electrons behave in a normal way and the superelectrons are responsible for superconductivity. The number of electrons at any instant inside a superconductor is a constant, and as temperature decreases, the number of superelectrons increases, and as temperature increases from 0 Kelvin, the number of normal electrons increases. If I plot a graph with temperature for showing the variation of number of electrons inside a superconductor, and let this be the critical temperature. As the temperature decreases from critical temperature, the number of superelectrons increases. This shows the variation of superelectrons, and as temperature increases from 0 Kelvin to critical temperature, the number of normal electrons increases, and at any instant the sum of superelectrons and normal electrons is a constant. The superelectrons are responsible for superconductivity, and superelectrons carries almost the entire current through the superconductor. Actually, superelectrons and normal electrons flow parallel inside a superconductor, and superelectrons can easily be attracted by a small transitory electric field which creates inside the superconductor. And due to this small transitory electric field, the superelectrons inside the superconductor experience a force given by F is equal to minus EE. Let that be relation number 1. From Newton's second law, F is equal to ma, or F is equal to m dvs by dt. Let that be relation number 2. This Vs is the velocity, drift velocity of superelectrons, or comparing these two, we get m into dvs by dt is equal to minus EE, or dvs by dt is equal to minus EE divided by m. Let that be relation number 3. We have the relation connecting current and drift velocity as I is equal to NAVE. Here I use subscripts for I, N and V. So IS is supercurrent, NS is the concentration of superelectrons, and Vs is the drift velocity of superelectrons. From this expression I can write Js is equal to NSVSE. Here I put the negative sign because our charge carriers are electrons. Let that be relation number 4. And I take the time derivative of relation 4. I get dJs by dt is equal to minus ns E into dvs by dt. But we have dvs by dt is equal to minus EE by m. So djs by dt is equal to minus NSE into minus EE by m, or djs by dt is equal to ns E square by m into E. This expression is called first London equation. This is called first London equation, developed by two brothers, F. London and H. London. This is called the first London equation. According to this equation, if E is equal to 0, dj by dt is equal to 0, or js is equal to a constant. So even if the applied electric field is 0, even when the applied voltage is 0, the material can have a constant current density or a constant current. So in order to maintain a constant current inside a superconductor, the application of electric field or application of potential difference is not necessary. This fact that E is equal to 0 takes us to another thing. We know from Maxwell's equation, del cross E is equal to minus dou B by dou T. If E is equal to 0, if E is equal to 0, minus dou B by dou T is equal to 0, which implies B is equal to a constant inside the superconductor. But this is against Meissner effect. According to Meissner effect, in the superconducting state, the magnetic flux density or magnetic induction inside a superconductor is 0. Therefore, London brothers modified this equation 5. We can take the curl of equation 5. We can take the curl of equation 5, which gives del cross djs by dt is equal to del cross ns E square by m into E, or del cross djs by dt is equal to ns e square by m into del cross e. But we know del cross e is equal to minus dou b by dou t. Therefore, del cross djs by dt is equal to ns e square divided by m into minus dou b by dou t. Now I integrate this expression with respect to time, so I get del cross del cross js is equal to ns minus ns e square by m into b. This is called second London equation, and this is completely in agreement with Meissner effect. That is, when the magnetic field B is 0, del cross J is 0, that curl of current density is 0, which is in complete agreement with Meissner effect. Okay, London penetration depth. We have from Maxwell's equation del cross B is equal to mu 0 js. Let that be relation number 1. Taking the curl of this equation, del cross B is equal to del cross mu 0 js, or del cross B is equal to mu 0 into del cross js. Let that be relation number 2. Del cross B is the familiar vector identity. This del cross B is equal to del into del dot B minus del square B. It's the curl of a vector field is equal to the gradient of divergence of vector field minus del square the vector field. In our case, the vector field is magnetic field. Therefore, the curl of magnetic field is equal to the gradient of divergence of magnetic field minus del square B. But we know that del dot B is equal to 0 because magnetic monopoles do not exist. Therefore, del cross B is equal to minus del square B. Let that be relation number 3. So instead of del cross B, I can write minus del square B is equal to mu 0 del cross js. Let that be relation number 4. But we know that del cross js is equal to minus ns e square by m into b. This is actually the second London equation. So instead of del cross js, I can substitute equation 5, right hand side of equation 5. Then the equation 4 becomes minus del square B is equal to mu 0 into minus ns e square by m into b, or del square B is equal to mu 0 ns e square by m into b. Instead of this term mu 0 ns e square by m, I write 1 by lambda square. That is, del square B is equal to 1 by lambda square B. Let that be relation number 6, where lambda square is equal to m by mu 0 ns E square or lambda is equal to square root of m by mu 0 ns into E square. Equation 6 is a second order differential equation. The solution of the second order differential equation is straightforward. It is given by b of x is equal to b0 into exponential minus x by lambda, or e raised to minus x by lambda. That is equation 7. This equation shows that the magnetic field varies with distance in an exponential way. If we plot a graph with magnetic field along y-axis and distance along x-axis, we get a curve like this. This is the maximum magnetic field denoted by B0, and we take a point where the magnetic field is 1 by E times the maximum magnetic field. At this point, the magnetic field is 1 by E times the maximum magnetic field, and corresponding to this magnetic field, we get a distance denoted by lambda. This distance lambda is called penetration length or penetration depth. So what is penetration length or what is penetration depth? Penetration depth is the distance at which the magnetic field has a value 1 by E times the maximum magnetic field. If we apply magnetic field to a superconducting specimen, the magnetic field penetrates inside the material as the magnetic field is increased, and when the magnetic field is 1 by E times its maximum value, the distance inside the material through which the magnetic field penetrates is called penetration length and is denoted by lambda. It further indicates that this penetration is in complete agreement with Meissner effect. The penetration depth is verified in a number of cases and is found to be in agreement with its experimental value, which is about 500 angstrom. From this we can derive an empirical relation for penetration length, and is given by lambda, or lambda at t is equal to lambda 0 into 1 minus t raised to 4 divided by tc raised to 4 the whole raised to minus 1 by 2. An empirical relation for super electrons or superconducting electrons can also be obtained and is given by n at temperature T. Actually it is ns, it is ns is equal to n0 into 1 minus t raised to 4 divided by t raised to c, where ns is the number of super electrons and n0 is the number of ordinary electrons, and we can also define another parameter ns by n0 which is equal to w, called order parameter. If the temperature is greater than critical temperature, w is equal to 0, that is, there is no order. And if the temperature is less than critical temperature, the order parameter is not equal to 0, which means or which implies that there is a specific order for electrons inside the material which is related to entropy. Some definite sort of order exists inside the superconducting specimen for a temperature or for all temperatures less than superconducting temperature Tc. Isotope effect. The critical temperature of a material is found to change with isotopes. For different isotopes, the critical temperature is different. Actually, the critical temperature Tc is directly proportional to m raised to minus 1 by 2, where m is the isotopic mass. More recent experiments suggest another relation where Tc is proportional to m raised to minus alpha, where alpha is equal to dou log Tc divided by dou log m. Okay. We also know that the Debye temperature theta d is also proportional to m raised to minus 1 by 2. Let that be relation number 2. From these two relations we can write Tc proportional to the Debye temperature theta d, or Tc by theta d is equal to a constant. This equation implies that while taking into consideration the critical temperature, while calculating the critical temperature for the theoretical development of superconductivity, we should take into consideration the lattice interaction also, because the Debye temperature is also found to related to critical temperature, and this Debye temperature theta d is related to lattice interaction.